Here's the proper way to find the horizontal asymptotes of a function by using limits at infinity. The trick to finding horizontal asymptotes is to figure out what happens to the function as x gets big and we go really far to the right, which is also called determining the end behavior of the function. In fancy math language, this is written as taking the limit of a function as x approaches infinity. If you've never seen or understood limits before, it's okay. All this limit means is plug in infinity for x and see what happens. In this example, we get something pretty messy, which we need to simplify by remembering some rules about infinity. In general, anything involving infinity, whether it's adding, subtracting, multiplying, or dividing, will still be infinity. The one important exception is that dividing a number by infinity will always be 0, as long as it's not infinity divided by infinity, which is undefined. In this case, our limit simplifies to infinity divided by infinity, which is undefined. But whenever a limit is undefined, it usually means we can do more work with algebra tricks to rewrite it in a way that is defined. In the case of rational functions, a good algebra trick is to divide both the top and the bottom by the highest effective power of x, which in this case is x to the third. After simplifying the fractions a bit, we can now take the limit by plugging in infinity for x and see that a lot of these terms will be 0, since they are a number divided by infinity. This eventually gives us 0 over 1, which is just 0. So we can say that this function will approach y equals 0 as we go really far to the right, and thus the function has a horizontal asymptote at y equals 0. Here's a different example, where we'll end up having a non-zero horizontal asymptote. This time, we're just going to start off with our algebra trick and divide everything by the highest effective power of x, which is x to the fourth. And then we're going to simplify. Now we take the limit at infinity by plugging in infinity for x, and notice that these two far right terms will go to 0, since they are a number divided by infinity. This leaves us with 3 divided by -6, which simplifies to -1/2. So we can say that this function will approach y equals -1/2 as we go really far to the right. And thus the function has a horizontal asymptote at y equals -1/2. Now there's one special case you have to look out for when finding horizontal asymptotes, and this occurs when the highest effective power of x on the top is exactly 1 more than the highest effective power on the bottom. When this happens, we need to do polynomial long division first before taking our limit at infinity. In this example, the highest effective power is 2 on the top and 1 on the bottom, which is a difference of 1. So we're going to rewrite this fraction by doing polynomial long division. Doing so gets us what looks like the equation of a line, 2x minus 4, plus a remainder, 12 divided by x plus 2. This remainder can be thought of some error that keeps the function away from touching the line. If we focus just on the remainder, we can see that taking the limit at infinity causes the remainder to go to 0. This creates what we call a slant asymptote, because as x gets really big, the remainder starts to disappear, and the function looks more and more just like the equation of a line, which in this case is 2x minus 4. So now we can say that there is a slant asymptote at y equals 2x minus 4, and you're done. Keep in mind that even though the function reduces asymptotically to a slanted line, the end behavior will still be infinite since the line goes up into infinity. Now let's look at the last type of horizontal asymptote. You may be wondering why I keep saying the highest effective power of x. Well, that's because you can't always just look at what's the biggest number in the exponent. Take this function, for example. At first glance, it would seem that the highest effective power of x is 8, since that's the biggest number we see in the exponents. However, there is a square root on the bottom x to the 8, which will end up cutting its effective power to 4. This is because square roots are the same as raising a number to the 1/2. And if we remember our exponent rules, raising a power to a power multiplies the powers together. This means that our new highest effective power is 6, which is still more than 1 greater than the 4 on the bottom. So we don't need to do polynomial long division, and we're just going to start by dividing both the top and bottom by x to the 6. Quick tip, when putting exponents back inside square roots, you need to double the exponent. So dividing by x to the 6 becomes dividing by x to the 12th. Now we can simplify our fractions and take the limit by plugging in infinity for x. Doing so is going to get rid of a lot of terms because we're just dividing by infinity. So now we're just going to be left with a 3 on the top and a 0 on the bottom. Technically, 3 divided by 0 is undefined, since it could be positive or negative infinity. It depends whether the 3 is being divided by a really small positive number or a really small negative number. But in either case, the function does not approach a real number, and as we go really far to the right, x becomes infinity. So we can say that there are no horizontal asymptotes, and you're done. And there you have it. That's how to find horizontal asymptotes with limits.
Nice!